Welcome to the deep dive. Today we are opening up a real cornerstone text of modern physics, Richard Feynman's lectures on physics.
That's right.
And we're diving into, well, the fundamental mystery at the heart of the universe. Chapter 37, Quantum Behavior.
It really is foundational stuff. You could argue this chapter is maybe the clearest introduction to quantum mechanics ever put down on paper. Feynman just strips away all the usual complexity.
No atoms, no fields.
Exactly. None of that. He zeroes in on just one thing, the electron, to show precisely where our everyday classical thinking completely falls apart.
So the mission today is to get our heads around why that happens using these three simple thought experiments Feynman lays out.
Yeah, the famous two-slit setup, but in 3 variations. It's brilliant, really.
He sets up this comparison. You've got a wall, 2 holes in it, hole 1 and hole 2, and then a screen behind it to detect what comes through. And we're going to shoot 3 different things at it. First, just ordinary particles, then classical waves, and finally, the star of the show, electrons.
Okay, so let's start with the classical world. Get the baseline rules clear.
Right. First step, bullets. Imagine, like, a machine gun spraying bullets kind of randomly towards that wall.
Okay, very classical. Bullets are particles. They arrive in definite lumps, right? One hit at a time.
Exactly. And what we measure is the probability, the chance that a bullet lands at any given spot on that backstop screen.
So if you just open hole 1,
You get a nice smooth curve of hits, call it P1, peaks right behind hole 1, then tails off. Makes sense.
and just hole 2 open gives you a similar curve, P2, centered behind hole 2.
Yep. Now, here's the classical punchline. Open both holes. What happens?
For bullets, it's just simple addition. The total probability, P12, is just P1 plus P2.
Q1 plus P2, that's it.
That's it. No interference. Because, each bullet definitely went through either hole 1 or hole 2, not both. There's no mystery there.
Perfectly logical. Okay, baseline established. Now, swap the machine gun for, say, a wave source, like ripples in a water tank.
A wave tank. And now we're not measuring individual hits, we're measuring the wave intensity, how high the wave is at each point.
And waves, well, they behave very differently, don't they?
Oh, completely. When a wave goes through both holes, the parts of the wave recombine on the other side, they interact.
And that's interference.
That's interference. And critically, the total intensity you measure, I12, is not just I1 plus I2.
Right, this is where it gets interesting even classically. You see these patterns.
Yeah, peaks and troughs.
Yeah.
Where the waves arrive crest to crest, they add up. That's constructive interference. Big intensity.
And where they arrive crest to trough.
They cancel out.
Yeah.
Destructive interference. You get areas with almost no wave intensity at all. The math involves adding the wave amplitudes first, which allows for this cancellation, before you figure out the final intensity.
So, okay, recap. Particles add probabilities. Waves add amplitudes, which gives interference. Got it.
2 clear, distinct sets of rules. Now, for the main event.
The electron gun. We repeat the experiment, but this time with electrons. Fundamental particles. We turn it on, watch the detector.
And what's the very first thing you notice?
They arrive like particles. You hear these distinct clicks on the detector, click, click, click. They arrive in definite lumps, just like the bullets.
Undeniably, particles and how they arrive. But, and this is the big but,
But when you let it run for a while and look at the overall pattern of where those clicks landed.
the distribution, the probability curve, P12, it looks exactly like the water wave interference pattern.
Hold on, that makes no sense. If they're particles arriving one by one, how can they possibly create a pattern that requires wave-like interference? That needs something going through both slits at once.
That is the central mystery of quantum mechanics laid bare. If electrons were just tiny bullets, P12 would equal P1 plus P2. Simple addition.
But it doesn't.
It doesn't. It shows the peaks and troughs of interference. So the electrons, even though they arrive as particles, must somehow know about both slits. They behave statistically like waves.
So Feynman's proposition A, the simple idea that each electron must go through either hole 1 or hole 2, that has to be wrong.
It has to be false. At least it's false when we're not looking. The electron's behavior somehow involves both possibilities simultaneously to create that pattern.
Okay, wow. When you're not looking. So what happens if we do look?
Ah, the crucial question. How do we peek? Feynman suggests setting up a light source right by the slits.
Like a little lamp?
Kind of. The idea is if an electron goes past, it scatters some light. If we see a flash near hole 1, we know it went that way. A flash near hole 2, it went that way. We try to determine the path.
Okay, makes sense. We're watching now what happens to the pattern.
And here's the absolute shocker. The moment you can tell which path the electron took, the moment you watch it by scattering that light, poof, the interference pattern
It's
vanishes.
gone.
Gone, completely. The distribution of clicks snaps back to the classical bullet pattern. P12 becomes just P1 plus P2, the simple sum.
So the very act of observing which hole it went through forces it to behave like a simple particle again.
Precisely. The interaction needed to get the which path information, even just scattering a single photon, disturbs the electron enough to destroy the delicate interference effect.
That feels really weird, almost philosophical, like the electron knows we're watching.
Feynman is very clear on this. It's not a flaw in our measurement. It's a fundamental feature of how reality works at this scale. Observation isn't passive. It's an active part of the process. It changes the outcome.
We have to give up on predicting exactly what one electron will do.
Absolutely. And we need new rules. Rules that explain when things act like waves, add amplitudes, and when they act like particles, add probabilities.
Okay, so rule number 1 has to do with probability itself, right? It's not straightforward anymore.
Right. We can't just use simple probability. We need this mathematical tool called the probability amplitude, usually written as the rho or the Greek letter phi.
And this isn't probability itself.
No, it's like a potential for probability, the complex number, which is key.
Complex number, meaning it has 2 parts.
Yeah, think of it like having a magnitude and a direction, or a phase. The magnitude tells you how much, kind of like loudness for a waves. The phase tells you where it is in its cycle, like the position of a crest.
Ah, and that phase part is what allows for interference, adding things that can cancel out.
Exactly. You add these amplitudes together first. Then, to get the actual real-world probability, P, you take the magnitude of that final amplitude and square it. P equals the absolute square of Fittipar.
Okay, so that's how interference math works. Amplitude Fittipar, square it for probability P. What's the second rule? The one about observation.
That's the rule of alternatives. It tells us when to add amplitudes versus probabilities. It hinges on distinguishability.
Distinguishability, meaning, can we tell the paths apart?
Precisely. If an event like an electron arriving at the screen can happen in multiple ways, like via hole 1 or hole 2, and those ways are fundamentally indistinguishable.
Meaning there's absolutely no way, even in principle, to know which path was taken.
Then you add the amplitudes first, phi phi 1 plus phi 2, and then square to find the probability. P equals phi 1 plus phi 2, that gives you interference.
Okay. Indistinguishable paths add amplitudes, interference, and the flip side.
If you could distinguish the paths, if an experiment is set up, like with our light source, where it's possible to know which alternative happened.
Even if you don't actually look at the result, just the possibility is enough.
Just the possibility. If the information is available, even in principle, then you lose the interference. You have to calculate the probability for each path separately.
Okay.
P dollar equals phi 2, P dollar equals phi 2, and then add the probabilities. P equals P1 plus P2. Back to classical behavior.
Wow. So the potential to know destroys the quantum weirdness, but couldn't we be really clever? Design some super gentle way to peak that doesn't disturb things enough to wreck the pattern? Try to cheat the system?
You'd think so. But nature has a built-in safeguard against that, and that's the Heisenberg Uncertainty Principle.
Okay, Heisenberg. This says you can't know everything perfectly at the same time.
Exactly. Specifically, you cannot simultaneously know both the exact position and the exact momentum of a particle with infinite precision. There's a fundamental limit.
The more precisely you know one, the less precisely you know the other.
That's the trade-off. The product of the uncertainties in position and momentum has to be greater than or equal to a very small, fixed number related to Planck's constant. It's a law of nature, not just bad measuring tools.
So how does that stop us from cheating in the two-slit experiment? If we try to pinpoint the electron's position really accurately to see which slit it passed?
To get high position accuracy, delta small, you need to probe it with something that has a very short wavelength, like high-energy light.
Right. Short wavelength, high-energy photon.
But hitting the electron with a high-energy photon gives it a significant and, more importantly, random kick. It changes its momentum unpredictably.
Ah, so measuring the position precisely messes up the momentum?
It messes it up by just the right amount. That random kick changes the electron's trajectory after it passes the slit.
And that change smears out the pattern.
It smears it out perfectly.
Yeah.
The math works out such that the uncertainty introduced in momentum is just enough to wash away the interference peaks and troughs. The pattern disappears precisely because you tried to determine the path accurately.
So the uncertainty principle acts like a rule enforcer. It guarantees that you can't know the path and see the interference at the same time.
It protects the consistency of quantum mechanics.
Hmm.
You can have particle information, which path, or you can have wave information, interference, but you fundamentally cannot have both simultaneously with perfect clarity.
It's like the limits on what we can know are actually woven into reality itself.
That's a great way to put it. It's deep.
Okay, let's recap. We saw three key things today. Classical particles, like bullets, just add probabilities. Simple.
P12 equals P1 plus P2.
Classical waves add amplitudes first, which leads to that characteristic interference pattern.
Peaks and troughs. Intensity isn't just the sum.
And then electrons, the quantum mystery. They arrive like particles, but their pattern shows wave interference. They add amplitudes.
Unless you watch them.
Unless you watch them, if you know, or even could know, which path they took, the interference vanishes, and they just add probabilities like classical particles.
And the uncertainty principle is the fundamental reason why we can never beat this. Any attempt to see the path introduces enough uncertainty to destroy the wave pattern.
It's truly mind-bending.
And the big takeaway, as Feynman stresses, is that at this fundamental level, physics has to give up on certainty. We can only predict the probabilities, the odds of what might happen. Determinism, the idea that we could know the future if we knew everything now, just doesn't hold.
Thank you for joining us on this deep dive into the absolute weirdness of quantum behavior. Here's something to maybe chew on. If everything is made of these strange quantum things like electrons, why do everyday objects, big things like us or billiard balls, seem to follow such simple, predictable, classical rules? Why don't we show interference patterns?
Yeah, that's a good question to ponder.
We'll leave that one hanging for you to explore.